The simplest type of I/O on any type of microcontroller is called parallel port I/O. We will refer to them as parallel I/O ports. A PIC24 microcontroller can have multiple parallel I/O ports that are named port A, port B, port C, etc. Each is 16 bits, and the number of PIO pins that are available depend upon the particular PIC24 microcontroller and its package. For our particular microcontroller, we have the following parallel I/O pins available. Port A, bits 4 through 0. Port B, bits 15 through 0. Each pin on these ports can be configured to function as either an input or an output. The data direction is controlled by a corresponding bit in the tris register that corresponds to that port. For example, the tris A special function register controls the directions of port A, while the tris B special function register controls the direction of port B. There's another special function register that is associated with the I/O port that's called the lat register. For example, lat A or lat B. This register is going to hold the last value that was written to this port. You can treat the port B and tris B special function registers as simply 16-bit variables in your code. For example, here tris B is assigned the value 00FF. This means that the upper 8 bits of port Z will all be outputs because their corresponding tris bits are all zeros, while the lower 8 bits of port B would all be inputs because their corresponding bits in tris B are 1. The way that you can remember that, if a tris B bit is a 0, then that means output. O for output. If it's a 1, it's an input. In this case right here, we're assigning port B the value 8000. That would mean that assuming that all bits of port B were outputs, that would mean that RB15 and RB13 would be high because this written in binary is 101 for that upper 4 bits. The rest of the outputs would all be low. This code right here is testing one input on port B, the least significant input on port B, and seeing if it's equal to 0. While you can read port B like this as a 16-bit variable, we're going to use a different style in which we're going to write code that explicitly names the single bits that we are testing. When reading or writing single bits, we're going to use this style to name the bits. Underscore RB0 refers to port pin B0. Underscore RB1 refers to port pin B1, and so forth. So for example, this code right here is in a while loop that's waiting for the value on pin RB2 to become non-zero. As long as it's 0, it's going to loop in this loop right here. Here, it's looping in this loop while pin RB3 is a 1. Whenever it goes to a 0, it will exit and continue on. Before we go any further, let's try to understand how a parallel I/O pin can function as either an input or an output via the tris bit setting. By the way, tris is shorthand for a tri-state. So we need to review what a tri-state buffer is. This device right here is a tri-state buffer. It has an input A, another input called output enable, and an output Y. We can view a tri-state buffer as being a buffer with a switch on its output. When output enable is a 0, the switch is closed. That means that when this is a 0, whatever's on A is going to flow through here without any problems. However, if output enable is a 1, then that means that the switch is open and whatever is here cannot get to the output. The output is disabled, and it means that this output is floating, which is typically designated as a Z state. It could either be a 0 or 1. It's not being driven. Inside the parallel port logic of PIC24, there's a latch that can change the tris bit setting that basically is controlling the output of the tri-state driver. There's another latch that's going to be used to actually drive a value onto the actual pin. So in this case right here, if the tris bit is a 0, then that means this driver is enabled, and whatever I write to this latch here is going to drive through here and appear in this output. If I actually wanted to send this bit to another PIC, I would need to configure this input as I would need to configure this pin here as an input. In order to configure as an input, I would need to set this tris bit here to a 1, which means that this buffer here is going to be disabled. It's like it's physically disconnected from this. So whatever I drive here would come in here, and I would actually see it when I would read this particular port. If I was going the other direction, then I would want to have this PIC24 here configure this port as an output and configure this port here as an input. So this is showing you how bidirectional communication can be accomplished by using these tri-state buffers on pins that can be configured to either be an input or an output. This is called bidirectional half-duplex communication because communication can only go in one direction at a time. It's either going from this PIC24 to this PIC24, or it's going from this PIC24 to this PIC24. We can't communicate in both directions at the same time. This diagram here shows a generic hardware diagram for a parallel I/O pin. Let's see if we can make some sense of it. This latch right here contains the value of the tris bit. The tris stands for tri-state. We recall that when we wrote a 0 to this latch, we configured this port as an output. Let's see why that works. If we follow this through, we'll see that the 0 will appear here. By the way, these muxes are present because an external pin on the PIC can be shared with other modules on the PIC24. So we want to configure this port as an output, so we wrote a 0 to the tris bit, means that there's a 0 on this pin right here. This buffer right here is called a tri-state buffer. And when there's a 0 in here, it means it's enabled, and whatever appears on this input here, be it a 1 or a 0, is going to be driven out through here and is going to appear in this output. Well, where is this coming from? If we drive this thing back, it's coming from this latch. This latch right here is what we're going to write to whenever we want to drive something out in this output pin. It's called the lat bit. It's also the same. It's also the port bit. This can be, for example, this can be lat B0. It can also be RB0. Writes to either lat B0 or RB0 go to the same D flip-flop in the port. So writing a 0 or a 1 here, as long as this tris bit's a 0, that 0 or a 1 will appear out and drive through to the output pin. Let's talk about a read operation. If I want to read the value of this pin here, then I need to do a read of the RB bit, for example RB0. That will read the physical voltage on the pin. If this pin is configured as an output, then what I'm reading is I'm reading whatever the voltage is on this particular pin as I'm driving it. If this pin is configured to be an input and to be configured as an input, this would be a 1 here, and the tris latch, which would come out here, it'd be a 1 on this output enable of this tri-state buffer, which disable it. In that case, I would be reading whatever something else is driving this IO pin, not what I'm driving, if this pin was configured as an input. I could also read the lat bit. If I read the lat bit, what I'm doing is I'm reading the last thing that I wrote to the port. I'm not reading the physical pin voltage. If I read lat bit, for example, if I read a lat B0, I'm reading the last thing that I wrote, not necessarily what the value of this IO pin voltage is. I can also read the tris bit. If I read the tris bit, I'm simply reading the last thing that I wrote to the tris bit, to the tris latch. Let's talk a little bit more about the difference between the lat bit and the port bit. Writing the lat bit is the same as writing the port bit. Both writes go to the same place. Both writes, writing the lat bit or the port bit, go to this latch right here, which would, if that's configured as an output, would drive the output pin. Reading the lat bit is different from reading the port bit. Reading the lat bit is reading the last thing that I wrote. Reading the port pin is reading the equivalent digital I/O value of this I/O pin. If there's a high voltage here, it would be read as a 1. If it's a low voltage here, or 0 volt, it would be read as a 0. When could reading the lat bit return a different value from reading the port bit? It can be done in this way. I could short the output pin to ground by tying it directly to ground. That means that this pin here would always, if I read it, would always return a digital 0 because it would always read a digital 0V. If I wrote the lat bit though as a 1, then when I read the lat bit, I would read back what I just wrote, which would be a 1. By the way, if you ever short an external pin to ground like this, do never configure this pin as an output and then try and drive it high. If you configure this pin as an output and try and drive it high, you can draw an excessive amount of current through the port and can damage that port pin. We said in the previous slide that writing a lat bit and writing the port bit goes to the same place, and it does. Writing both of those actually go, both writes go to the same latch. So it would seem that writing a port bit, we could either use underscore lat or underscore RB, whichever one we'd want. However, that's not going to be the case. We're going to always want to, when we're writing to a port, we're going to always want to use the lat B name. The reason we're doing that is because sometimes the compiler, if we're doing a single bit assignment like this, it will use a bit set, bit clear instructions for this write. It turns out that bit set and bit clear instructions are execute by doing first a read, then a modify the value, then a write back. In this case, when it does a read, it's going to read the value to lat, which is the last thing that we wrote. It's going to modify it, and then it's going to write. When we wrote it like this, it's going to read the port pin itself, then try to modify that, then try to write it. Where if we have the port pin configured as an output, it turns out that if we have successive bit sets like this, because of rise time and how fast these instructions execute, it might be that this bit set and bit clear will not give you the right value if we use this. So the bottom line is that when we're writing a port, we're going to always want to write to the lat bit. We're not going to want to write to the port bit. So let's say that again. When we're writing to a port, we're going to want to write to the lat bit here. We're not going to want to write to the port bit. Initially, we're going to use push button inputs to provide single bit inputs to our PIC24 and lab experiments. Here is the typical way that we're going to hook up our push button switch. We're going to have a pull-up resistor to our VDD with our push button switch connected from the pull-up resistor to the ground. When the switch is open, this pin is pulled up to VDD, so it's going to see a logic 1. When this push button is closed, it's shorting this pin to the ground, and we're going to see a logic 0 in this pin. What you don't want to do is you don't want to leave off a pull-up resistor like this, because when the switch is open like this pin would be floating, and there'd be an unknown voltage in that pin, and it could read either a 0 or a 1. The previous slide mentioned that when using a push button switch, we needed an external pull-up so that when the push button was not pressed, the pull-up was pulling the floating input up to VDD. It turns out that it's a pain to have to wire up that external pull-up resistor, and since push button inputs are common for microcontrollers, the PIC24 designers designed each port to have an internal pull-up that can be enabled by a bit in a special function register. Each port pin, parallel port pin, has a corresponding special function register bit that will either enable or disable the pull-up resistor. Whenever we're using a push button input on a parallel input pin, we will always enable that internal pull-up resistor. You never want to use a push button switch without some form of pull-up resistor, either internal or external. It turns out that the pull-up resistor is actually implemented by a PMOS transistor inside the port. Most external pins on the PIC24 are actually shared between different on-chip modules. Whenever sharing or using a particular pin, we need to be careful to disable other functionality that may be present on that pin. For example, RB15 also shares a pin with the analog to digital converter. What that means is that whenever we're using this pin as a digital input or output, we have to disable the analog functionality by setting a particular bit in a special function register. We're going to try and hide this functionality from you via macros, which we'll talk about in a future slide. Some parallel I/O pins can also be configured to be an open drain output, which means that the pull-up transistor normally found in a PMOS driver is removed or is disabled. What this means is the pin can only pull low. If you try and pull high, it simply means that this switch right here will be open, but nothing will be pulling high, so it'll just be floating. In that case, why would an open drain output be useful? Here's one application. Perhaps you have a PIC24 running at 3.3 volts that needs to communicate with the device that requires a 5-volt input. You can configure this PIO pin to be an open drain output. When you're pulling low, it's fine. It's going to short this transistor to be a 0 here, and I'll pull this thing to low. If I want to pull to 5 volts, then whenever I try to drive high, this pin here will be floating as a Z. I will add an external pull-up resistor out here to 5 volts, and this pull-up resistor here will provide the necessary 5 volts. If you use this particular application of trying to provide a 5-volt output, you need to make sure that this particular PIO pin is also 5-volt tolerant. Some PIO pins are 5-volt tolerant. They can withstand 5 volts on their outputs, while others are not. Recall that in the startup schematic for the PIC24 that we used for the first hardware lab, that we had RB15 port was used to drive a dual purpose LED, one that served as a power LED and one that served as a blinky LED for a heartbeat, and we configured this pin as open drain. How did this actually work? Well, here we're showing RB15 configures open drain, and we configured the heartbeat LED like this, which is in series of resistor to VDD, and we connected RB15 at this point right here. What happens when we try to drive this thing low? In other words, we're going to 0 to the port. That means that this inverter here is going to make this a 1, closing this switch. We're going to put that's going to cause this to go to 0 volts here. We're shorting this to ground. All this current flowing through the resistor is going to go this direction. No current will be for the LED. So the LED would be off. Why do we have this resistor here in the first place? It's to act as a current limit. This particular value of 910 ohms, if we take 3 volts divided by 910s, it turns out that we'll have about 3.6 milliamps flowing through this. That's going to be less than the maximum 4 milliamps port current that a PIC24H device can sync, and so that's why that's why we have a 910 ohm resistor here. So to summarize, whenever you put a 0 here, that means that's going to close the switch at this point, grounding this output to 0 volts, syncing all the current this direction, no current flowing to the LED, so the LED would be off. When lat B15 is a 1, it means that this switch right here is going to be open. Our open drain configuration is disabled the pull up, which means that there's nothing on this port able to pull this guy up. However, our external pull up will be pulling it up. That means that all the current flowing through here, this is going to be very, very high resistance here. There'll be almost no current flowing in there. Almost all the current will be flowing through the LED, which means the LED will be on. We want to emphasize that the RB15 open drain configuration for the heartbeat LED was a special case, as we were trying to make one LED serve 2 purposes. In other lab experiments, we're going to hook up LEDs to output ports, and in all of those cases, we're going to hook up the LED like this, in which the output port is simply going to be configured as a normal output driver that's either going to drive high or low. This resistor right here is going to be used to limit the current. In this configuration, the LED is going to have some voltage drop across it, which means that this resistance here can be lower than what was used for the heartbeat LED. For convenience and portability purposes, we're going to supply some macros and inline functions for you that will hide pin configuration details. For example, config RB15 as dig output will configure that port as a digital output. Config RB15 as dig input will configure that pin as a digital input. We have macros supplied for each port pin, and they take care of the details of configuring these pins. Other port configuration macros that we're going to provide for you are listed here. For example, to enable the RB15 pull-up, we could use this. To disable the pull-up, we'd do that. To enable an open drain configuration of the pin, this is the macro that would be used. To disable the open drain, this is the macro. We also have macros that sort of combine some other macros. For example, config RB8 as digital open drain output will configure as an output and also enable the open drain feature. So these are the general forms of these macros, and they can be found in our port header files.